We've now covered Roth's theorem, so that's Szemerédi's theorem for progressions of length 3, which tells us that a dense subset of 1 to n, as long as n is large enough, contains an arithmetic progression of length 3, large enough in terms of the density. I now want to give you, or over the next few videos, I want to give you an idea of how to prove that, a pretty good idea of how to prove that in the case of progressions of length 4, which is quite a lot harder. I'm not actually going to give a proof of Szemerédi's theorem for progressions of length 4, but I'm going to give an alternative, I'm going to give a proof of a similar statement in a slightly different context. I'll prove that a dense subset of fp to the n, if p is a prime greater than or equal to 5, contains an arithmetic progression of length 4. And the ideas of the proof are very similar to the integer case. It's just that quite a lot of technical details become a lot easier in the fp to the n case. So for example, in Roth's theorem, the business of having not just a, but the middle third of a equaling b and c, and then in order to deal with problems that happen when you pass to subprogressions and passing to modular arithmetic and back to the integers and things, those kinds of difficulties don't arise. And various other things that work more cleanly. And since it's really the ideas that I want to convey rather than the technical details of the proof, this seems like a good thing to do, I think. But the first thing I want to do is explain why it is that the Fourier approach, in a certain sense, breaks down when we get to progressions of length 4. And so what I'm going to look at, so we are working still in fp to the n. I'm looking at subsets of fp to the n. P is a prime greater than or equal to 5. By the way, there's nothing terribly fascinating about p having to be greater than or equal to 5. It is actually important in some arguments that p is co-primed to 2 and co-primed to 3. We'll see various points where that is important. But in particular, it's important if you just want to be able to define an arithmetic progression of length 4 at all. So if you've got a set a plus d, a plus 2d, a plus 3d, where we're interpreting a and d as elements of fp to the n, well, if p is 2, then 2d is going to be 0. So a and a plus 2d will be the same, and a plus d and a plus 3d will be the same. And similarly, if p is 3, then a and a plus 3d will be the same number. So it won't really be a progression of length 4, it'll be a progression of length 3 with a sort of duplicated beginning and end. Actually, you can ask yourself the question, if you look at a dense subset of f3 to the n, do we get a progression of length 3? And the answer is yes. And it's an exercise to prove that just by copying the proof of Roth's theorem and then changing a few details. So you use Fourier analysis over f3 to the n instead of Fourier analysis over Zn, and you'll find that actually the details are a lot cleaner and easier over f3 to the n than they are over the integers. I may put that as a question on an example sheet, actually. That was first noticed by Roy Meshulam. So that is regarded as a theorem of Meshulam. So that's subsets of f3 to the n finding progressions of length 3. And there's a long story associated with those and the bounds and that kind of thing, which I'm not actually going to do in this course. But if you Google capset problem, then you will find lots of links to that very nice story. Quite recent story as well. Okay, so what is the example that shows that Fourier analysis, or an example that shows that Fourier analysis runs into problems? I'm going to take the following set. So recall that we define x dot y, if x and y are elements of fp to the n, that just means sum over all I, xi, yi, where that's a sum inside fp. So now let's take a, so we're thinking of p as fixed always and n as tending to infinity, and I think of p as maybe even equal to 5. So a, let's take the set of all x such that x dot x equals 0. Because it's a mod p in a product, you know, there's no problem with x dot x being 0. It doesn't mean that x has to be 0 or anything like that. Certainly very, very far from it. So this is a same way, right? It's just a way of saying sigma xi squared equals 0. This is the same condition. So this is a quadratic condition. We have a quadratic polynomial that has to take a particular value. I could just as easily have taken some other value here, but it's convenient to take 0. And we're going to see that this set here has, apart from at 0 itself, has only extremely small Fourier coefficients, and yet it will turn out not to contain roughly the expected number of progressions of length 4. So Fourier analysis will not tell us, or sets that are sort of quasi-random from the point of view of progressions of length 3 are not necessarily quasi-random from the point of view of progressions of length 4. So it's not enough to have small Fourier coefficients for us to be able to say a lot about how many progressions A contains. Okay, so how does the proof go? Well, we've got to calculate the Fourier coefficients of A. So we've got to look at an expression of the form. So I'll let omega equal e to the 2 pi I over p. And so now we're going to look at A hat r, which is the average over all x of ax, which I will write as 1 x dot x equals 0 omega to the minus r dot x. Now this 1 x dot x equals 0 I want to rewrite. So that's an element of fp, and I'm going to use the fact that if, say, w is in fp, then sum over all lambda in fp, let's make it average rather, average over all lambda in fp of omega to the lambda w equals, if w is not 0, well, 0 if w doesn't equal 0, and 1 if w does equal 0. If w does equal 0, we just get 0 here. Omega to the 0 is 1, and we get 1. So I'm going to write this as average over all x, average over all lambda in fp. This is a little trick to make things look nice and clean, of omega to the lambda x dot x, omega to the minus r dot x. So we can clean that up a little bit. Average over all, I'll interchange these expectations, and I won't bother keep writing in fp. We just hope you remember that that belongs to fp, whereas this one belongs to fp to the n, omega to the lambda x minus r dot x. Now, in order to get an idea of the size of this, I'm going to look at the size of this thing here. So, and in order to look at the size of this thing here, I'm going to look at its modulus squared. This is another standard trick. So for each lambda, we have that omega lambda x minus r dot x squared equals the average over all x and y. By the way, if you want to be an additive combinatorialist, you need to get very, very used to expanding out absolute values squared of sums. And so how do you do it? You take the variable inside and you duplicate it. So I've got an x here, so I have now an x and a y. and you write out the expression for x, and then I'll do it in 2 steps here. So you write out whatever you have for x, and then the complex conjugate for y. So I should have y there. Which, let's just quickly do some calculations. So that's omega lambda x dot x minus y dot y, and minus r dot x minus y. And this has got a factor x minus y in a sort of dot product sense. Omega to the lambda x plus y dot, this is x plus y dot x minus y because the dot product is symmetric. So I can just put that in there and then go x minus y. And now I can change variables, another absolutely standard trick. So I can have u equals x plus y, v equals x minus y, and we see that that's an invertible transformation. We can recover x plus y and x minus y from, sorry, we can recover x and y from x plus y and x minus y because p is not 2, it's an odd prime. So that is omega to the lambda u minus r dot v. And if which way around should I do it? I'll say if v equals 0, the expectation over u is 1. If v does not equal 0, the expectation over u is 0 unless lambda equals 0, in which case it is omega to the minus r dot v. Yeah, I think that'll do. And now I wonder whether it's better to do it the other way around. But I'll leave it like that. So so if lambda does not equal 0, then I'm wondering whether I really want to switch it around to the other way. I'm going to just try it the other way in case that makes it nicer. That's what I did but when I was preparing this. So the other way around will say if lambda u minus r equals 0, then expectation over v is 1. Otherwise it is 0. That the probability lambda u equals r equals p to the minus n. So I'm picking that's a probability if I pick a random u, unless lambda equals 0, in which case it is 0 if r doesn't equal 0, and 1 if r equals 0. So if lambda equals r equals naught, we get 1, and otherwise at most p to the minus n. So for this quantity here, so that implies that if r doesn't equal 0, the average over lambda of the average over x of omega, where was this expression, omega lambda minus u dot lambda x minus r dot x is less than or equal to the number of lambdas, which is p, in fact it's the number of non-zero lambdas, but that p times the size of each one of these things. When I squared it, I got p to the minus n, so p to the minus n over 2. Which is very, very small when n is large. And if r equals 0, then we get a contribution when lambda equals 0 of 1. So then it differs from 1 over p, because that happens with probability 1 over p, by at most p times p to the minus n over 2 by the same estimate. So what that tells us is that a hat of 0 is very, very close to 1 over p, differs by at most that, and a hat of r is very small for all r not equal to 0. So a has, apart from the trivial Fourier coefficient, so basically that's telling us, this thing here is telling us that a has density almost exactly 1 over p. So the probability that sum of the xi squareds, where is it? It's up here. The probability that sum of the squares of the xi's is 0. It's pretty much uniformly distributed, actually, as it turns out. Not terribly surprising. In other words, if I choose a random x, sum up the squares of the coordinates, I'm going to get each possible value with roughly equal probability. In particular, I'll get 0 with probability roughly 1 over p. All the other Fourier coefficients are small, so it has positive density, and those Fourier coefficients are small. But now let's have a look at, so now we make the following observation, which is that x dot x minus 3 x plus d x plus d plus 3x plus 2d dot x plus 2d minus x plus 3d x plus 3d. So you'll recognize Pascal triangle coefficients here. Equals 0. You can check that very easily, and you can even think hard and see conceptually why it's the case. It's connected with taking a sequence, taking some quadratic sequence and taking a different sequence once and then twice and then a third time, and that kills it off. And it's the same sort of phenomenon going on here, except we've got dots. And so that tells us that if this is 0 and this is 0 and this is 0, then this must be 0. In other words, if you've got the first 3 terms of an arithmetic progression, so if x, x plus d, and x plus 2d all belong to A, that implies that x plus 3d belongs to A. And if you work a little bit harder, you can see that the probability that those 3 belong to A, well, actually no, we've done it. The Fourier coefficients are all tiny, so the probability that those 3 belong to A is almost exactly the density cubed, so 1 over p cubed. And so the probability that all 4 belong to A is roughly 1 over p cubed, whereas if A behaved like a random set of density 1 over p, we should be getting 1 over p to the 4. So it turns out that arithmetic progressions of length 4 can be sort of detect, in a certain sense, can detect quadratically defined sets. And that's going to be a significant theme for the rest of the course. It's the appearance of quadratic functions when we start looking at longer progressions. And so, well, one wouldn't necessarily despair there, because what we found was that for progressions of length 3, what we wanted to show was that if the number of progressions is not roughly what you expect for a random set, then you can find some r such that the average over x, ax omega to the minus r dot x is large. So in the fp to the n context, it'll be this r dot x. And the same proof shows quite easily that you can get such an r not equal to 0. And we can think of this as a linear, so these r's, that'll be sort of sigma ri xi, that's a linear function of x, linear map from fp to the n to fp. So what we have here is something called a linear phase function. Now we've seen that this a, well, it has a distinct correlation with a quadratic function. So we had in this particular case ax, well, we can show that omega minus x dot x is large for this particular set A that I defined up here. So one might ask, can we do some kind of what you might call quadratic Fourier analysis? So here we have linear polynomials that correlate with x, or linear polynomials in the exponent such that this resulting function correlates with x. Now we'd like to find quadratic functions, and so they don't have to be quite as simple as this one. And we're going to show that actually, yes, that is the case. But the proof is a lot more complicated, because whereas in the linear case what you can just do is expand A in terms of its Fourier coefficients and do simple inequality to argue that at least one of those Fourier coefficients has to be large. There's no such thing as expanding A in terms of its quadratic Fourier coefficients. The linear ones, the characters form a basis, but these sort of what you might call quadratic characters, they very definitely don't form a basis for all sorts of reasons. And one very simple reason is that there are too many of them. There are more than p to the n of them. But there are other reasons, like there's a notion of rank of, if the quadratic form has low rank, then it won't actually be, well, they're not orthogonal to each other, but they won't even be approximately orthogonal. They have low rank. So there are all sorts of complications that come in. So we've got to do something much more non-obvious in order to identify the quadratic functions that arise. And in order to do that, I have to introduce a whole new story, and that is some objects called uniformity norms. I'm going to introduce these gradually. I could define them just straight off, but instead I'm going to talk first of all about uniformity norms just in the context of what we already know about progressions of length 3. So you'll remember that the expression well, we showed that this was a rather important thing because it's somehow related to additive quadruples. So it equals average over x plus y equals z plus w, fx, fy, fz bar, fw bar. And we can write this in all sorts of ways, and so I'm actually going to. Another way we wrote it was x minus y equals z minus w, fx, fy bar, fz bar, fw. And we can also write it in the following way by changing variables slightly. It's equal to f of x plus a, f of x plus b, f of x plus a plus b. And another nice way, which I actually slightly prefer to the one above, x minus a, x minus b, fx minus a minus b. I'm just changing variables and then sort of renaming them to the changed variables. And another way we can write it, if we look at it back to here, it's f star f, f star f, or which is the same thing as f star f L2 norm squared. And we can also think of it as f star, well, I won't bother writing it, I'll just do it in this form, f star 2 squared. I've not told you what f star is, where f star of x equals f of minus x bar. I don't think I'm going to prove that this is the same as everything else, because it's a simple exercise and it's rather useful, rather a good thing to do. But I mean, if you just look at this expression here, and maybe, or perhaps this one here, okay, well, I'll just write one more expression. So this thing here could also be written as average over x, y, and a. So I'm going to substitute y as x minus b. So we get f of x minus a, f of y minus a. So if you write it this like that, then I think it becomes quite easy to show that it's equal to this, because that is a convolution of f with f star evaluated at a. Okay, so we've got all those different ways of thinking about this thing here, and because of that, and actually that's not the only reason, we're going to call it fu2 raised to the power 4. Why are we calling it fu2 raised to the power 4? Because it's the fourth power of a norm, which we see very easily from this expression here, although it can be proved without Fourier analysis, as we'll see later on. So we'll call it that, and so we call, if we haven't got the fourth power, we say this is the u2 norm of f. So the fourth root of all these things is the u2 norm of f. And of course, the 2 there suggests that there might be something called a u3 norm, and you might even, if you pick the right one of these expressions, you might even be able to guess what the u3 norm is, but I'm not going to tell you that just yet. Instead, I'm going now to prove a lemma let G be a group of odd order and let f1, f2 and f3 all be functions from G to the complex numbers. Oh, I haven't really said what I'm trying to do, so actually I don't want to, well, I'll state the lemma since I've started, but there was a remark I wanted to make first, but I'll make that just after I've stated it. So here's an expression that I think you can see is highly relevant to arithmetic progressions of length 3. Actually, I think motivating this lemma after I've stated it does actually make some sense, so I'm not too disappointed that I forgot. So that's less than or equal to the 2 norm of f1 times the u2 norm of f2 times the u2 norm of f3. So what we have seen is that if f equals, so this is not part of the lemma, if A is a subset of G and A has density delta, then A contains roughly delta cubed G squared progressions of length 3 if A hat of R is small for all R not equal to 0. Perhaps I should say A chi is... Actually, we haven't really seen that, but we saw it in the Zn case, and the proof works it generalizes straightforwardly. I suppose we'll see something similar in a moment. It generalizes straightforwardly to the subsets of any group of odd order. Now, let's just think about, if you remember, towards the end of the proof of Roth's theorem, we introduced what I called the balanced function, which was f equals a minus delta, and we observed that f hat of 0 equals 0, and f hat of r, or chi, let's say, equals a hat of chi, if chi is not the trivial character, which I've denoted by 0. So the condition that a hat of chi is small for all chi not equal to 0 is simply saying that the L infinity norm of f hat is small. So a condition for A to contain roughly the expected number of progressions of length 3 is that the L infinity norm of the balanced function should be small. Now we get the following simple inequalities. That the fourth power of the L infinity norm of this balanced function f is certainly less than or equal to the fourth power of the L4 norm of f, because that's the sum of the fourth powers of the Fourier coefficients, and that's the largest one raised to the fourth power. So the largest one raised to the fourth power is at most the sum of all of them. That is certainly at most the maximum Fourier coefficient of f squared multiplied by the sum of the squares of the other one, sum of the squares of the Fourier coefficients of f. And since f takes values in -1 up to 1, all Fourier coefficients are definitely at most 1, so that's at most the L2 norm of f. And so that thing here equals, this, what I meant to say was, this by Parseval equals the L2 norm of f squared, and since f takes values in -1, 1, the L2 norm of f squared is at most 1, so we can put that that's at most the L infinity norm hat squared. So this we can also write as u2 to the fourth. So it tells us that the fourth power of the u2 norm is sandwiched between the fourth power of the largest Fourier coefficient and the square of the largest Fourier coefficient. So that sort of makes them not exactly equivalent, but equivalent in the sense that if one of these things is small, then so is the other one. If this is small, that's got to be pretty small. It may only be the square root of this, so it can be a bit bigger, but it's nevertheless, if this goes to 0, this has to go to 0 as well. And if this one is small, then of course this one is small because it's smaller than this. So they go to 0 together, even if not necessarily at exactly the same speed. so that tells us that this statement here, that you get roughly the right number of arithmetic progressions of length 3 if all the characters are small, if all the Fourier coefficients are small. We can also deduce that if this quantity is small, then A contains roughly the number of progressions of length 3. But the advantage of this statement is, so if the fourth power of the U2 norm is small, then we get that average AX plus D, AX plus 2D is approximately delta cubed. But I haven't mentioned Fourier analysis anywhere there, because I can define the U2 norm. Let's go back and have a look at it. Without any mention of Fourier coefficients. Only mention them here. All these ones have nothing to do with Fourier coefficients. So that raises the question, can we actually prove this result directly? The result that if that is small, then that approximation holds. Can we prove it without using Fourier analysis? And the answer is yes. And that's helpful because if we want to generalize the progressions of length 4, we don't have Fourier analysis. We can't just take the Fourier transform for reasons I've just mentioned. So having an alternative argument, or at least, yes, an alternative argument which might potentially generalize the progressions of length 4 is very reassuring. So what I'm going to show is, well, here it is. I'm going to start by proving this lemma here. I'd better rewrite what the lemma says. Well, perhaps I don't have to rewrite it actually. Let's just get going. So f1x, f2x plus d, f3x plus 2d. Doesn't really matter what bound we're aiming for, because we're just going to use it. What really matters is what techniques we're going to use. I might just stick a modulus around, because I think I said, even though f is going to be real in the case that we apply it, I did say that I had some functions that go to the complex numbers, so I'll stick a mod squared sign around it. And by the way, why have I done the modulus squared? It's just because modulus of a complex number is a horrible function, whereas a modulus squared is not a horrible function. Because we can expand it out and that kind of thing. So I'm going to use Cauchy-Schwarz to start with and say that that is, I'll rewrite, perhaps I'll just to make it clearer how I'm doing Cauchy-Schwarz. I'll just rewrite it as average over x of f1 of x, average over d of f2x plus d, f3x plus d. So Cauchy-Schwarz will tell me that that's at most the average. So the two functions that I've got as my product are f1 of x and the average over d of f2 of x plus d, f3 of x plus d, which is a function of x. So we get f1 of x squared to the half, but I've squared it, so don't have to do that square root. And now I have the average over x, average over d of f2 of x plus d, f3 of x plus 2d squared. So that part here is just the L2 norm of f1 squared, and if we just look up here, we had the L2 norm of f1, and the squared has just come from the fact that I've squared the thing I'm trying to bound. So that's great, we've got that there. So let's concentrate on the second term. So second term equals the average over x, the average over d and d dashed. So again, I'm just using my habitual sort of multiplying out squares of modulus instinct. So f2x plus d, f2x plus d dashed bar f3x plus 2d, f3x plus 2d dashed bar. And now I'm going to change variables, and I'm going to let d dashed equal d minus c. So I get average over x, average over d and c, f2 of x, oops, f2 of x plus d, f2 of x plus d minus c bar, f3 of x plus 2d, f3 of x plus 2d minus 2c bar. And now I'm going to introduce some notation. If I've got a function f, perhaps I call it g, but I call it f because I haven't got f here. So if I write delta a f of x, that is shorthand for f of x times f of x minus a bar. Why this partial sign? It's because if x happens to be of the if f of x is omega to the phi of x, say it's a, so this is just a little explanation of notation, then partial dA f of x equals omega to the phi x minus phi of x minus a. So it's a kind of bit like a discrete derivative, so to speak. So you're taking a difference between phi of x and phi of x minus a. So that's why this is a nice notation to use. So anyway, using that notation, this expression here is equal to e of x, e of dc. Now that here is partial c f2 of x plus d, and that one here is partial 2c f3 of x plus 2d. And if you look at the pairs of the form x plus d, x plus 2d, because again g has odd order, those actually just are uniformly distributed over all pairs. If I take sort of u and v, there's a unique solution to x plus d equals u, x plus 2d equals v. So I can rewrite this as the average over c, and then the average over all x and y of partial c f2x, partial 2c f3 of y. And perhaps I can rewrite that as, I can take the ey into, move that over, partial c f2x ey partial, and I'll put them in brackets just to make it absolutely clear what's happening. And now it's really tempting to apply Cauchy-Schwarz again, so I'm going to, that's less than or equal to average of c, average of x, partial c, f2 of x squared to the half, and average over c, average over y, partial 2c f3 y bar squared to the half. And now let's look at just this first bracket, and I'll forget that half for the moment. So this thing here equals, and yet again I'm going to just multiply out one of these things, so I get average x. Hope you forgive me for using a y, just why not? Delta c f2x, delta c f2y bar. And actually I would rather call that y an x plus a. So let's put an a there and make that y. Maybe even x minus a would be nicer. So I'm allowed to do that. That's still going to range over all pairs of variables. So that's just rewriting it completely. So it's average of x, a, c, and then we have, I'll put c, a, f2 of x, f2 of x minus c bar, and then here we get f2 of x minus a bar, f2 of x minus a minus c. Oh, x minus c minus a, it looks nicer to write it that way. And that was one of the expressions, except I've got c and a instead of a and b. Let's go right back to it's one of these. It's this one here. So that is equal to f2 u2 to the fourth. And you notice that I squared this term, and I had previously squared, where's it gone? Well, I started off by squaring the original term, so this fourth power is again what I want. And if I run through exactly the same argument, I'll have the same thing but with 2c replacing c, but 2c, because g has odd order, runs over the group just as the same way that c does, so that I get that, well, I finished basically, I get that this expression is at most f3 u2 to the 4, and putting all that together does indeed give me that this expression here is at most f1 2 f2 u2 f3 u2. Okay, I'm going to finish this video now, but I'm going to give you a little advance notice. Oh no, wait a minute, sorry, there is one more thing I want to do. So how do we get from that to arithmetic progressions? It's not very difficult. So now let's just have a look at the expression ex d ax plus d ax plus 2d, and we're remembering that a is equal to delta plus the balanced function of a, and we're going to make an assumptions about the u2 norm of the balanced function. So that equals average xd of delta plus f of x, delta plus f of x plus d, delta plus f of x plus 2d. And this thing here is a sum of 16 terms, each of the form f1 of x. I said, sorry, 16, I'm jumping ahead to progressions of length 4. 8 terms, f1 of x, f2 of x plus d, f3 of x plus 2d, where f1 is either delta or f, f2 is either delta or f, and f3 is either delta or f. Now let's think about those 8 terms. If I choose delta for all 3 of them, so we get from this, if I choose delta from each bracket, I get delta cubed. Supposing I choose delta from this one, delta from this one, and just the f from this one, then I'm averaging over all f of x plus 2d, but the average of f is 0. So I'll get 0 if I choose one f from one of the brackets and 2 deltas. What if I choose 2 f's? Well, let's think about what happens if I choose f of x and f of x plus d. Then I get delta times the average over xd of f of x times f of x plus d, but x and x plus d range over all pairs, so that's the same as delta times the average of f of x times the average of f of y, and again it's 0. And the same thing f of x and f of y, because 2D, because G has odd order, 2D is the same as D, and so pairs x plus 2D also range over the group uniformly. So again we get 0. So the only way that we can not get 0 is actually f of x plus d, f of x plus 2d. That is going to be a slightly more complicated statement we'll hold when we come to talk about progression to length 4, but it doesn't matter too much. So the main result of this video, which will then be generalized in the next one, tells us how good this approximation is, that minus delta cubed is less than or equal to that which we've already bounded by, in modulus, by f2 times fu2 times f of u2. So at most that. And if we just remind ourselves that f of u2 squared, where's it gone? I've lost it. Here we are. So f of u2 squared is at most the f hat of infinity by this inequality here, which was very simple. So we can actually also deduce, and this is at most 1, so brackets, because we're not really trying to talk about Fourier analysis. It happens also to be at most this. And that was essentially the bound that we got out of the Fourier approach. And actually you can improve it slightly because f2 is more like, it's related to the density of A rather than, it's sort of not far off root delta or something like that, I think. So the bound that we get out of this approach is pretty similar to the bound that we get from the Fourier approach. Great, so we'll carry on in this vein next time. It'll be a shorter video next time, actually, because unless I add a few things to it. Yeah, actually, I think maybe it won't be shorter. I can think of some things that I will want to say, but I must stop now. Thank you very much for your attention.